Hi, and welcome to our new session here in our Bayesian optimization chapter, which is on Gaussian process surrogates. So, what are actually surrogate models? Well, I guess we have discussed that. So that's a regression model that helps us to model our underlying cost function in HPO. But maybe we can talk a little bit about, the desired characteristics of such a surrogate model. I guess there are many different forms of regression models in machine learning. What kind of a regression model would we like our surrogate model to be? So usually this is supposed to be a nonlinear and a local model, so a model that can really model local structures, because we are assuming that our underlying cost function represented by our computer experiment is not going to be too simple. So usually using something like a linear model is not going to be too appropriate. It should hopefully form accurate predictions, especially for small sample sizes, because we will not see too many design points over the course of optimizing our expensive black box. And as you will see later on, uncertainty estimates are usually required. So we will not only need a posterior mean prediction, but also something like a posterior standard deviation, a posterior variance. And hopefully the model should be quite robust. So yeah, it should work well without any human modeler intervention. So it should run automatically in our Bayesian optimization loop and not crash or, query back to the human modeler about some, choices for the model, so to speak. Depending on the application and the configuration space, it should usually also be able to handle different types of inputs. So we already discussed there can be numerical or categorical inputs, or there could even be dependencies on our configuration space. So it could even be of a hierarchical nature. So what is the intuition now for the Gaussian process? So I will only be able to cover them here quite briefly. You might want to go to a, full book or a longer tutorial. So for example, there's the very famous Rasmussen and Williamson book, Gaussian processes for machine learning. I can recommend that very heavily in this, but this will take a little bit more time than, just 15 minutes. So what is a Gaussian process? Well, it is a regression model, but it's a specific one. Maybe you can already see this from the process in Gaussian process. So this is based on a stochastic process, and this stochastic process can actually model distributions over functions, which, let me actually see if my pen is still working. It's not. So maybe I have to click here. Yeah, it's working now again. Sorry for that. So a Gaussian process enables us to actually model complete distributions over functions. For a Gaussian process, one of its defining properties is that for any finite set of input points, x1 to xn, the vector of modeled function values is actually jointly Gaussian. So these guys here, these predicted outputs at these n training points, or actually it doesn't even have to be training points, n points under consideration is always a multivariate Gaussian. And in a certain sense, the Gaussian process is defined by this property that every finite dimensional margin distribution is a multivariate Gaussian. If you then think about this a bit more, you can see that the Gaussian process, or in everything we're interested in with respect to its, stochastic properties, anything we would ever like to compute based on this Gaussian process is fully specified and characterized by a mean function and a so-called covariance kernel that encodes the correlation, or the covariance of outputs between two specified points x and x dash. So this kernel, this encodes how correlated the outputs of nearby points are. We'll look at this a bit more in detail on the upcoming slides. So while the theory of Gaussian processes actually comes from stochastic processes, and a full theoretical treatment of Gaussian process is, not too simple. If you're only willing to invest, a couple of minutes and your, background in probability theory, it's, maybe a little bit weaker. We will see that training a Gaussian process and predicting a Gaussian process on finite data, and I guess that's what we usually do in applications, and when we implement these things, we usually have to work with finite data, but this simply, quote unquote, boils down to linear algebra on the multivariate Gaussian. And I guess I don't have to put too many air quotes around simple here, because computing on the multivariate Gaussian is not the most complicated thing in existence. So how can we now specify the Gaussian process model a little bit more formally? So as I've already said, it represents a prior over functions. So usually we simply just notationally denote it like that here. So our function is now a random variable, our f. And this is a sample from a Gaussian process with a specific mean function and a specific covariance kernel. The observation model looks like that. So the idea is that the output that we observe is generated by putting a function f on some observation x and potentially adding in some IID noise epsilon I. So I will talk about these noisy observations a little bit more later on in an upcoming subchapter on noisy Bayesian optimization. I've incorporated this here already because the formulas don't become much more complex if we already talk about this now. But as I've said before, for our simplified first approach for Bayesian optimization, I'm going to assume that this thing here is not there or that it's zero. And then if we would do that, we'll later on see that then we are willing to interpolate our data. And this is also exactly what happens with such a Gaussian process model, where the posterior passes exactly through our training data points. We can incorporate this variance term here of our epsilon noise terms into the Gaussian process model, and then we are effectively creating a regression model where the uncertainty never shrinks to zero at our training points. As you will see, I will talk a lot about covariance kernels in the upcoming slides. I won't talk too much about this mean function m of x here, and the reason for that is that, well, from a technical perspective, we'll just assume that this is going to be zero. And this is, I don't know, in many books and papers, you very often see statements like, we're going to use a zero mean Gaussian process. The reason for that is that, well, we can actually do something like integrated trend estimation in our Gaussian process model. So it's actually possible to put some kind of a trend function here into the GP and to estimate its parameters. I don't know, some form of a linear or quadratic form of a trend. But a very simple solution is to simply center and standardize the observed training data points. And after this centering, they will be zero mean. And then use a zero mean Gaussian process on this. And you will see that this is usually enough to create a fully, local nonlinear type of model that can pretty much handle data of arbitrary complexity. So what are we now mainly interested in? Well, we're mainly interested in how we can form a probabilistic prediction at an arbitrary test input x with our Gaussian process. And as you can see, in a certain sense, we can directly write this down without potentially doing any form of training. We'll discuss what's really going on there in a few minutes. But the idea is now to look at it in the following manner. So if we look at a certain test point, and we now look at the output modeled by our Gaussian process, y of x. So this is going to be now a univariate Gaussian, because this is a one-dimensional marginal distribution. We said every finite dimensional marginal distribution of a GP is Gaussian. So this is a normal distribution. And of course, because we're doing this for a test point, after we have seen some training data already, this is going to be conditional on the training data that we have seen. And in order now to get a full probabilistic characterization, to get the complete conditional predictive distribution of a Gaussian process, the only things we're interested in are here this mean part of this posterior Gaussian, mu hat of x, and the posterior variance sigma hat squared of x. So if you can write down formulas for these two guys, we are done. We know the complete posterior distribution at our query point, at our test point x. And as it turns out, you can directly and nicely compute them just by doing this little bit of linear algebra here, which I'm not going to read out. So let's see if we can begin to at least understand what is meant by the notation here. So let's start with y. So bold y is simply the vector of observed outputs. Yeah? So we have an n-dimensional training set, just put together all of the observed output values here in this vector bold y. Capital K, also not hard to understand. This is our so-called kernel matrix. You can also call this, I don't know, covariance matrix, or you can call this a gram matrix in kernel techniques. So this is simply a matrix where for every I, j entry, we evaluate our kernel function k, and then we plug in the resulting value into this matrix here. And k star and k star star are of a similar nature. So k star is a vector. Again, struggling with my pen here. So k star simply evaluates the covariance kernel between our given test point and any training point. So this is an n-dimensional vector. And k star star is the so-called, I don't know, self-similarity. This is just the kernel evaluated on the test point with respect to itself. So, and you can hopefully see that if you're given a certain kernel function, you can encode, produce all of these objects here, and then you can do this computation here. And, well, and here. Now, so, and because of that, we can now also do a first analysis of the computational complexity of a Gaussian process prediction. So how would you actually compute that? So as you can see here, you have to form pretty much, I don't know, some vector matrix products. And there is this very annoying inverse here going on regarding the kernel matrix. Inverting matrices is always bad numerically. So usually we do something else. So we can also do a Cholesky decomposition for this symmetric matrix, and the cost of that is pretty much n cubed. And if we have the Cholesky decomposition of our kernel matrix, we can cache that if we want to predict on multiple test points. And then, so we have to do this once for multiple test points. And usually we don't want to predict on a single point, we want to predict on multiple points on a test set. So we do this O of n cubed computation once to get the Cholesky decomposition. And then we have to spend O of n for each posterior mean computation for a test point, and O of n squared for the variance computation. Many people, I don't know, simply say, yeah, Gaussian process prediction is of cubic time complexity. Yeah? Then they're talking about this Cholesky thing here, yeah, to handle the inversion of these two guys. Okay. So these were a bunch of potentially very unintuitive formulas, and we have no idea where they come from. So like I said, I can't go into too many details here in this introductory chapter, but what I do want to say is that it's actually not very hard to come up with these formulas yourself. So what you can actually do is you can write down an m-dimensional vector where you put in all of the y output values that you're observing in your training data, and you're also, I don't know, in a formal manner, you put in there an n+1 entry for your test point. So you now have an n+1 dimensional random variable, random vector. And because this vector comes from a Gaussian process, this is an n+1 dimensional multivariate Gaussian. Has a zero mean, because we're assuming that. And you can compute. You can actually directly write down how the covariance matrix of that Gaussian looks like, because it's simply the covariance between any two pairs of points, which we simply abbreviated with this kernel matrix capital K here and with these K star and K star star guys. Yeah? So this is pretty much just writing down, okay, that's the correlation computed by our kernel. Yeah? So there's like really nothing going on there. And the major thing you now have to do, and this is what I meant before with that it all boils down to simple linear algebra on the multivariate Gaussian, is then now coming up with the insight that what you are pretty much, what you are interested in is the conditional distribution of this 1D thing here, y of x, based on the training outputs, yeah, with this, which is this n-dimensional vector. But this means simply have to convert a fully specified n+1 dimensional multivariate Gaussian into a conditional distribution where you take one component and you condition on the other ones. But we know, I don't know, from pretty much any book that covers, I don't know, multivariate distributions in probability theory or statistics, that for any type of conditioning that you can do on pretty much an arbitrary block structure here in your multivariate Gaussian, there's a simple formula that now computes the conditional distribution. And this is exactly what we did here. Go to any book on probability theory, look up the formulas, do this yourself. This is actually very nice, a little exercise to get, I don't know, less scared by these complicated looking formulas. It's not hard to derive this and come up with the predictive formulas of the GP yourself. And from this you can also see that apparently now your posterior mean vector mu hat is actually a linear combination of the training outputs weighted by this guy here. I can see this directly from the formula. This posterior variance is in a certain sense the prior variance at the test point reduced by what the data tells us about the value y of x. And if this guy here is going to be 0, you can also very, very simply directly prove that we are going to create an interpolating model where the posterior variance at a design point, so at a point which is in the, could also say training point here, I guess for Gaussian processes, is going to be exactly 0, which means we are directly interpolating all of the training data. Well, I said we need something like a kernel to encode our covariance between two training points. And one of the most common examples here is the so-called RBF kernel. This is for radial basis function. Some people also call this the squared exponential kernel. And this is the formula. And as you can see, what this does, it computes a distance. So we are given now a pair of training data points, and we want to somehow encode, characterize how the correlation of these two guys looks like. And usually we do this based on the distance between our pair of training points, x and x dash. So what we do is, or the idea is the following. So the closer these points are together, in input space, the more correlated their output should be. I guess that's the smoothness assumption that we bake into the Gaussian process. So if points are very close together in x space, their y values should be very related, and they should be very similar because this function is somewhat smooth. And if they are very far apart in input space, maybe they are even nearly completely uncorrelated, because what happens here in this part of the input space is completely unrelated to what happens in this other far apart part of the input space. And we do this by now computing exactly this distance here. Here for the RBF kernel, we compute the Euclidean distance, but we also use a so-called length scale parameterization of the kernel. So you can see these LJ guys here, and these LJ guys are being used to weight the different feature components of this distance computation. So there's one LJ for each feature xj. So what we can do by that is using a larger LJ. So this is a longer range, a long range of correlation along feature j. And this usually means that the values in this dimension don't matter too much. I guess you can see this by driving this LJ guy to infinity. So let's say LJ is, I don't know, nearly infinity. Then doesn't even matter what kind of distance you observe here between these 2 points. The component in the sum is driven to 0. It's going to be very, very small. But if this LJ guy here is quite small, maybe even close to 0, even very, very small distances are going to be blown up and are going to be made very relevant. And because of this reason, some people, and we will be able to actually learn these LJ parameters from data. Some people call such kernels automatic relevancy detection kernels, so ARD kernels. There's a special isotropic case. So if all of these are the same, and then we have a so-called isotropic covariance structure, And if we use such a specific RBF kernel, you can actually show, it's a little bit harder, that all of the sampled paths are very smooth. So they're actually they're differentiable in infinite amount of times. This is, I guess, maybe a little bit unrealistic for response surfaces you might see in practice. You can still use this. It doesn't mean that this kernel works very badly, but yeah, I guess it's good to understand its properties. And here on the right-hand side, I have visualized how this kernel function looked like in 1D for a single feature with different settings here of this length scale parameter. So you can see how the correlation changes depending on the distance and depending on this L parameter here. But I guess you could hopefully guess that from this simple x minus distance formula divided by L. And here, maybe a little bit more interesting, you can see how 1D GP prior samples look like. So if you would use that kernel, and then I said that this represents a distribution over functions, how sampled function paths might look like. And you can see exactly what I said before. So if we use a very large L parameter, yeah, the functions become quite smooth. Yeah, so you have to see a very, very, I don't know, large distance for it to matter, so to speak, in this feature dimension. And if we use a very small L value, even short distances matter. And because of this reason you can, I don't know, sample and model very, very, I don't know, wiggly, oscillating types of functions. There's also the so-called Matern family. This is a little bit more common in practice that people use this. The formula is a little bit more complicated. I'm not going to read that out. Again, you can see this automatic relevancy detection structure here. There's a, I don't know, hyperparameter of that kernel called nu that controls the smoothness of the sample paths of Gaussian processes modeled by this Matern family here. And yeah, I've written down different settings of this mu parameter. So if this is, for example, set to 0.5, then our functions are not even one-time differentiable. This would also be called then the exponential kernel, and it's a Brownian motion-like type of function that is modeled by this specific kernel. If we set nu to 1.5, it's one-time differentiable, and if it's set to 2.5, it's 2 times differentiable. You could see this as, I don't know, a reasonable assumption for most functions you could, I don't know, meet there out in the wild. Yeah, so I guess this is usually the default that we use in BO. I'm not saying that some people don't use other kernels for other situations or try out different kernels, how well they work. And here you can again see the visualization with the different new settings. I also wanted to visualize this a little bit in 2D. So here you can see a Gaussian process with a Matern type of kernel fit on some points, I guess 12. And again, we're using this 2D Brownian function as a toy example. And you can see the true cost function, which is our Brownian function now. You can see here the posterior mean in 2D. You can also see the posterior standard deviation. And in both of these plots here, I've also obviously plotted the training data. And you can again see that this Gaussian process here interpolates the observation in terms of its posterior mean, and it smoothly extrapolates between them. And you can also see how this posterior standard deviation goes down to 0 at the training points, and it grows with the distance from the design points. So the further we move away from the bulk of the data, the higher the uncertainty becomes, and this is exactly what we like in a BO context. Some further visualizations with respect to these length scales. So I guess it's intuitive to not only see this in 1D, I've done this here again in 2D. So here, again, on the Brownian function, you can see what happens if I use different settings for my length scales. So I can use an isotropic setting where I'm using the same L for both dimensions. You can see that if I use now a small L, the function I'm modeling becomes quite wiggly. So there are many local structures I'm willing to model, and the function becomes quite bumpy and wiggly. If I'm using a larger L, the function is way smoother and changes way more slowly. across this 2D input space. But what is potentially most interesting is if we look at a sector which is non-isotropic, where I'm using a small L1 and a large L2. And in such a case, again, you can see that the function changes fast along lambda 1, so into this direction, but slowly into this direction here for lambda 2, because my L1 setting is quite small and my L2 setting is quite large. And this means that our X2 feature, so to speak, is less relevant here in this case. And the idea is to actually learn that from data. And we can do that with GPs, and this is quite nice about this, which is why I'm explaining this on this slide here now. So this is all about how we can learn kernel hyperparameters. I guess this terminology is maybe a little bit confusing. You could also see these as the fundamental parameters of our Gaussian process that we want to learn. So, and yeah, usually these correspond to these length scales here. Maybe this also corresponds to the variance of the noise component if you are using a regression approach. And how are we going to train these, learn these? Well, we do something very, very common in machine learning. We look at the log marginal likelihood of the observed data. And again, this looks like a very scary and complicated formula. It's not. Write down the distribution of your training data in terms of its multivariate Gaussian. Write down its likelihood, take the log, simplify a little bit, and you will end up with exactly this formula. And again, this is a very, very good exercise if you have never done this before. And it's also, again, not very hard to do this with pen and paper. And this first term here, this is actually there, so it rewards fitting the data. So this becomes optimal, so to speak, or if you take the negative log likelihood, becomes small when our Gaussian process fits the data very well. And this second term here pretty much penalizes model complexity. So you could also see this as, I don't know, a regularized risk approach in machine learning modeling. And this last thing here is pretty much just a constant, so we don't really care about this. And this log marginal likelihood you can now optimize numerically. You can also figure out that this is pretty much a differentiable function in the parameters theta, and then you can optimize this numerically with any gradient-based technique of your choice. For example, I know you could do something like gradient descent or whatever, or run Adam on it. You can also run something like BFGS on it. That's kind of a standard. And usually you do this with a multi-start BFGS version, because this thing here is not going to be convex, but it's going to be quite multimodal. Again, we can discuss the cost now of training a Gaussian process. So for that, we could discuss how expensive it actually is to evaluate this guy here. So this log marginal likelihood, I guess we have to evaluate it if you want to optimize it. And again, we can see that the most annoying part in there is this inverting of the kernel matrix. And again, we would do a Cholesky for that. We would cache that and reuse this when we optimize over the log marginal likelihood. And again, this is cubic in the size of the training data. So you can also do this with a full Bayesian treatment via MCMC, so Markov chain Monte Carlo or Hamiltonian Monte Carlo, which is going to be even more expensive. Maybe a few words on mixed and hierarchical configuration spaces. So vanilla GPs usually only can deal with numeric inputs. We've already discussed that AutoML configuration spaces are somewhat messier. So for integer hyperparameters, what you can do is you can treat them as continuous during the GP fit and then simply round to the nearest integer before evaluation. For categorical hyperparameters, you can do this common one-hot encoding trick and then put a continuous kernel on the now continuous space, so to speak. This is quite simple, but it somewhat distorts distances. Or you can use a more appropriate Hamming kernel by modeling the correlation between the categorical parts, so to speak, of your configuration through such a, I don't know, binary evaluation where you say, okay, it's correlated with 1 if a level in one categorical feature, or if the level in a certain categorical feature is exactly the same between x and x dash. And if the level is not the same, then we would say it's 0. And then the most common idea is to model the numerical part with a numerical kernel, as we have seen this before, RBF kernel or a Matern kernel, and then model the categorical stuff with such a hemikernel, and then form the product between the two as a composite kernel design, so to speak, and optimize over this. If you even have conditional and hierarchical hyperparameters, this is even worse. So you can do a very simple fix by imputing your non-active hyperparameters with a default or a sentinel value, something like this. Usually this does not work too well with Gaussian processes. I think this conditional hierarchical stuff is also not even implemented in, for example, toolboxes like Blowtorch. There are dedicated Gaussian process kernels for exactly all of these cases. So there's stuff for specifically categorical and integer parameters. There are R kernels for conditional things and tree structured dependencies and so on. Very often they make the quite complicated GP even more complicated and the fitting even slower. Yeah, read these papers. This is all quite interesting. In practice, this is used, let's see, at least a little bit less. And yeah, we might come to the conclusion that random forests might handle these complicated structures a bit more naturally, and this is why we will also discuss them in an upcoming session here in this chapter. Okay, so let's do a summary with some GP pros and cons. So GP is a smooth, local, quite powerful estimator. It works very nicely on small data regimes. They give you well-calibrated uncertainty estimates that behave, hopefully, in exactly the manner you would like for optimizing expensive black boxes. And the posterior predictive distribution under the Gaussian process is normal, and we can exploit this in very many different ways. Some of them you will see here in this chapter. There are also some heavy cons. So as I've already said, GPs scale, unfortunately, cubically in the number of data points. They can handle numeric features natively, and for the other stuff we just discussed that, you have to do something special or live with crude heuristics. They're not that robust, so sometimes numerical problems can occur and might have to, program some special handling of these numerical problems, so you can use your GPs in an, automatic BO workflow, so to speak. And yeah, there's unfortunately also this question of which kernel to choose, how to set some, meta hyperparameters. You've seen this example, for example, for the Matern kernel, this kind of degree setting, that is a new thing. And if we now have to do AutoML to, run an AutoML procedure, that is maybe a little bit, problematic. Yeah, in practice, there are some default settings which work quite well, but it's still sometimes a bit unclear which, Gaussian process variant to use in what regime.